time. The next speaker is Joe Bramante, and he will be telling us about dark matter, new searches for ancient particles. So, Joe, I am forced to interrupt orally at the 5 minute before the end, but meanwhile, take it away.
Great, thanks very much, Keith. Very nice to be here. Today I'll be telling you a little bit about dark matter writ large, and then some new searches for, as I call them, ancient particles that I've done with colleagues and that my colleagues both in Canada and internationally are involved with right now. All right. Oh, yeah, I should say I'm at Queen's University, which is the Central University of the McDonald Institute, which is a new institute in Canada directed towards astroparticle research. And I also spend some time at Perimeter. So first, I'd like to talk about what do we know about dark matter writ large. Not much, but we do know a little bit. If I think about the mass of dark matter in GeV, the lower mass end is sort of limited by the smallest structures we see in the de Broglie wavelength or the Fermi degeneracy of either fermionic or bosonic dark matter. If I think about the high mass end and I want my dark matter to be a fundamental particle, I'm perhaps limited by the Planck mass unless I'm very adventurous in what I want to think about as the fundamental mass of a particle. When it comes to composites, the field is entirely open. I can think about composites made of bosons or to a lesser extent, composites made of fermions extending across this entire mass range. And in fact, if you look back at the dark matter literature, you'll find these candidates existing all the way back to the 80s when perhaps what we would today call a dark nucleus or a quark nugget was called a nucleorite. If I think about production of dark matter, this relates to what we don't know about dark matter yet, because if I think about the classic freeze-out WIMP, there's a specific set of temperatures I normally think about that gives me a classic freeze-out WIMP. If I think about a freeze-out variant, so something that follows the same sort of freeze-out pattern that we'll talk about in a second, we might call that WIMPish dark matter. I can really have that occur at a very wide range of temperatures, all the way from essentially a BBN temperature up to a temperature I might associate with the end of inflation. If I think about that temperature up at the end of inflation, I can actually just use a gravitational fluctuation to give me a very heavy dark matter particle. And if we want to hone in on why we don't really know exactly when dark matter was made or at what temperature or in what fashion, it relates to the fact that before BBN temperatures, we actually have very little information about our universe so far. We don't know if the universe was matter dominated, radiation dominated, inflation dominated, and this leads to a whole zoo of possibilities for how the dark matter could have been produced. Up at the highest energy range, you might say that there's a tensor limit if you want an inflationary cosmology. If you want to see more info about that, please see my grad student Simran Nerval's talk on Tuesday about Aslan and Platon gravitational wave probes of the early universe. So now that we've talked a little bit about dark matter's mass and its production, let's move on to its coupling to the standard model. There are a lot of different ways we could couple dark matter to the standard model. So as we said, it could be fundamental or composite. It could have essentially whatever spin you want as soon as you make it composite. And then I can think about it directly coupling to standard model fields like quarks, leptons, the hypercharged boson, weak boson, Higgs boson, so on. I can think about it mixing, much like neutrinos mix, or exactly like neutrinos mix in the standard model, with a standard model particle. And I could think about it coupling through a new dark sector intermediate field. And then I have lots of detection modes. Here I've arranged them in my own fashion, where I'm looking at detectors arranged from highest mass to lowest mass. This certainly isn't an exhaustive list. But if I think about the number of particles in GeV, I have interstellar gas clouds, stars, which actually have a lot of different detection modes, planets, which similarly have a lot of detection modes. Some experiments we're more used to thinking about, Super K, Ice Cube, Hawk, and Fermi. We have a great talk already from Knut Mora about direct detection methods for looking for dark matter. And if you think about the number of particles actually interacting with dark matter, in the case that you'd be producing dark matter at a collider or a beam dump, the number of particles you're talking about is actually quite small. So what about dark matter near us? Well, dark matter near us, as far as we can tell using gas data, using star data, has a velocity around 10 to the minus 3 times the speed of light. We can infer that near the large black hole at the center of our galaxy, its velocity would increase substantially. We have a few different models that have disagreement about what the dark matter density could be at the center of the galaxy. And this is entirely based on theoretical predictions where there isn't a lot of data in the center of the galaxy for us to tease out exactly what the dark matter density is, because the baryonic density kind of takes over, becomes much larger than the dark matter density. And so it's hard to say exactly what the dark matter density is. Some features that I'll emphasize because they're important for the rest of my talk are that there's also a local structure to the velocity of dark matter around us. By a main sequence star, there's a bit of a parametric coincidence that a main sequence star accelerates dark matter to about the same velocity that it already has in the halo. So it'll have about the same velocity around a main sequence star. Around a white dwarf, it'll have a velocity that's more like 0.05 times the speed of light. And around a neutron star, it'll have a velocity that's 0.7 times the speed of light. You can think about another thing, which is that there's also what you might call a local fine structure to dark matter. For instance, by Earth, you shouldn't expect to see any dark matter particles, modulo an exception I'll talk about later, that have a velocity below 11 kilometers per second. And that's because that's the escape velocity of Earth. So if you had a dark matter particle wander in, it should at least have the velocity you'd associate with the gravitational potential of the Earth, which is around 11 kilometers per second. So that brings me to a bit of a zoom in on the most classic touted dark matter production mechanism in the last few decades, which is the WIMP miracle. And this is that as the universe cools, dark matter falls out of thermal equilibrium and some portion annihilates the standard model particles. The miracle part of this is that if you look at the characteristic temperature, which only logarithmically depends on the dark matter mass over a certain range of masses, and you ask what's required of the cross section in order to give you the observed dark matter relic abundance, you'll find that if you couple a dark matter particle to a weak mass boson with a weak sort of a coupling, you'll get the right relic abundance. And then some symmetry arguments imply that there will be interactions at certain dark matter experiments. But one important caveat to that is that symmetry arguments require symmetry. And for example, electroweak symmetry in the standard model is broken. And that's something that we are associating this with when we talk about a WIMP miracle. And so we should keep our eye on that. But in a very generic sense, I could ask, what is the cross section for scattering on nucleons for a WIMP, for like a generic WIMP? And then parametrically, that would just be the weak structure constant squared times the reduced mass of the nucleon and the dark matter squared divided by the mass of a weak boson to the 4th power. And that comes out to roughly around 10 to the minus 39 centimeters squared, which seems to lie a bit above all of the existing dark matter searches. However, it's important to keep in mind that there are plenty of WIMPish models waiting to be found in the rest of the parameter space, and that this is really just a very specific example. To give you an example of a WIMPish model, or actually in this case, a very classic WIMP model that is still being sought out, let's talk about the Higgsino. Now, the Higgsino is motivated by supersymmetry. And so if you take all of the bosons in the standard model and you give them a spin 1/2 supersymmetric partner, those spin 1/2 supersymmetric partners will mix together after electroweak symmetry breaking. And if you're unfamiliar with neutralinos, but you're familiar with neutrinos, which are the spin 1/2 partners of the standard model gauge bosons, would mix together, all their neutral states would mix together the same way that you could think about neutrinos mixing together. If you learned about neutralinos first and then neutrinos second, then you already know what I'm talking about. But it's still important to remind ourselves that the Higgsino is actually a Dirac fermion, which means it can be broken into 2 Majorana fermion components. And that will happen in proportion to what the supersymmetric mass parameters M1, M2, and mu are set to. And so while before this breaking occurs, you'll have your Majorana component states of your Higgsino at a degenerate mass, so at the same mass. After that breaking, depending on what your supersymmetric parameters are, and for very simple supersymmetric parameters, you'll get a sizable splitting between your X1 and your X2 states. And this is symmetry, if you will, breaking this WIMP miracle. Because while you might expect that this particle, which couples directly to weak bosons because it's charged under the weak force, would give you 10 to the minus 39 centimeters squared. And that is actually the cross-section you should associate with it in the early universe when it's moving very fast. And this mass gap that would exist between x1 and x2 states wouldn't matter because it's moving relativistically. So that's a very tiny fraction of its energy and can easily have these interactions. If you're moving at 0.001 c, if you're moving at 10 to the minus 3 c, then this will be kinematically forbidden. You can't actually do this. You don't have a GeV worth of energy to make an x2 out of an x1. And this means that you're stuck thinking about loop suppressed scattering. And so you have to do a calculation including all the weak bosons in the standard model, and you have to be very careful and go to multi-loop order, which has been done by a number of groups of authors. And what you find is that the actual cross-section you predict in this model is extremely tiny. So depending on what your inelastic splitting is, this motivates a different class of searches. Specifically, it motivates high recoil inelastic searches. This is something I looked into with some collaborators back in 2016. And we showed what the state of affairs was. At the time, you could think about placing limits on inelastic splittings between Higgsino states of up to a few hundred keV. Now that's been extended a little farther. And recently I had some colleagues working on that. So you can see Ningyang Song's parallel talk if you want more information about that. So I'm also going to tell you a little bit later about neutron star searches for Higgsino dark matter. So we'll move on to different sorts of dark matter for the moment, but don't lose sight of the Higgsinos. All right, so the next thing I'm going to tell you about is diluted WIMP dark matter, which is quite often heavier. So here you have the exact same freeze out picture that you're used to. So you have some sort of state that's annihilating and giving you a relic abundance of some sort, except in this case, the story evolves in the following way. Let it freeze out to too large of an abundance, and then have some heavy state existing in the background. And that heavy state existing in the background is actually motivated by a lot of different beyond the standard model theories. There are a lot of theories that give you a matter-dominated epoch. The oldest theory I'm aware of that naturally bakes in this period of dilution where you have lots of decays is Affleck-Dine, where an Affleck-Dine field will have to decay to give you the baryon abundance of the universe, or the inflaton will have to decay to dilute the Affleck-Dine's baryon abundance, which tends to often be too large. And so in all these models, you tend to dilute abundances after they're sort of set in place. And if that sounds like a weird concept, you should be aware that this happens in the standard model anyway. When all the standard model states freeze out and decay, they are also diluting the abundance of everything in the universe, which is something you take into account when you actually do your dark matter relic abundance. And so something I looked into and found was that this would push the mass that you typically think about for your fundamental fermionic or fundamental bosonic dark matter up to a range extending into the multi-PeV or EV range, or 10 to the 6 to 10 to the 10 GeV range, using standard sort of freeze out arguments and a perturbative framework. And something we used to quantify how much dilution there was this little parameter zeta, which you'll see a little bit more in my slides. So I'll just mention that. It just quantifies how much you dilute the abundance after it freezes out. So this led to some recent work that I did with grad students Javier Acevedo and Alan Goodman, where we said, what are the implications of this for a simple model of composite dark matter, where fermionic dark matter couples through a light scalar, and at the end of its freeze out period, it'll go through a binding phase where it binds together and makes composite states, because that light scalar gives it a self-interaction that gives you bound states. This is something that was explored by a lot of authors in the last decade. And in the standard scenario with no dilution, you get composites of a certain size forming after these states freeze out. What we found is that with a very tiny amount of dilution, you start getting much, much more massive composite states. In fact, you get composite states which easily range with masses between milligrams and thousands of tons. This really opens up the mass frontier for what you should think about for a pretty simple dark matter scenario. In fact, we found that there are some really interesting signatures associated with such massive high number content composite dark matter states. the internal potential of these states will go like the mass of the dark matter outside of the composite divided by its self-coupling. And so that potential can be extremely large. It can be at levels of like 10 MeV or 100 MeV, which has really interesting consequences if you give it a very tiny coupling to nucleons. You'll get some pretty unique processes occurring inside the dark matter, including fusion, Bremsstrahlung, and the Migdal effect for even tinier couplings. And so this is something Javier Echeverria will talk about on Wednesday. But just the fact that there's this possibility that you can make these extremely large composite states means that we should entertain dark matter that has a very large cross-section and find out what happens if you have to deal with something that has a much, much larger cross-section and a much, much larger mass than you're naively expecting. And that brings us to multiscatter dark matter detection. So before I talk about multiscatter detection, I have to just talk about dark matter detection generally. And here you can think about a dark matter parallelogram, where there's a certain threshold that your dark matter search experiment can't get below. And so that sets a lower mass end to what you're sensitive to. Then there's a sensitivity limit that tends to increase linearly, although there are some exceptions to that as you go to high masses. Then you reach a certain mass where your experiment is flux limited, and you only expect to see a few heavy particles moving through your experiment during its entire exposure. And so you really can't think about discovering dark matter at a mass above that. And the last thing is the overburden, which perhaps is the least familiar concept to a broader audience. And that is just that the dark matter, when it's coming to your experiment, has to move through some quantity of material if it's underground or even if it's above ground. And that quantity of material can slow it down, especially if it interacts with matter a lot. And so that means that there will be some upper cross-section limit to what your experiment is sensitive to based on its threshold and the amount of material between it and the particle coming in. But there's a final thing to keep in mind, which is that in this sort of dark matter detection parallelogram, you can draw a horizontal line that separates the part of parameter space where you'd expect to see only one interaction in your detector and the part of parameter space where you'd expect to see many interactions in your detector, or a multi-scatter detection region. And this is just dependent on the proportions of your detector and the cross section you're thinking about. And yeah, this triple point here, if you look into it deeply, actually exists for most experiments that have reduced their backgrounds to near zero. I won't explain that, but I'd be happy to answer questions about it. So this brings us to underground multiscatter prospects. So with a bunch of these authors here, Ben Bromer in a grad student at Queens, Jason Kumar, Raphael Lang, Maxime Pospelov, and Nirmal Raj, we looked at how neutrino experiments could actually go look for this, along with direct detection experiments that are currently running. And in fact, Raphael Lang with a group of authors did some work where they just recast what you could do with existing Xenon 1-ton data in this multiscatter region. Something fun to think about is that at this boundary here, as far as I understand it, they're setting a bound using Xenon 1-ton data using the remote possibility at the very edge of this boundary that a particle which might interact a lot actually would randomly through Poisson statistics interact just once as it goes through the detector. Okay. That brings me to the flip side version of my talk, which is ancient searches for new particles. So with this knowledge and this understanding that we should be looking for dark matter in a variety of places, including at high masses and cross sections, me and a number of other authors have been looking at how you could reanalyze MICA data using overburden data. I'll leave that to be covered by Amit, where he'll tell you about plastic etch searches for dark matter. And that brings me to the second to last part of my talk, which is planets and stars as dark matter detectors. So this is quite interesting. So if you have dark matter that's very heavy, you can think about it scattering against the Earth a bunch of times and getting captured. And then there will be a first thermalization phase where it's in a wide orbit on the Earth, a second thermalization phase where it's on a small orbit on the Earth, and then it'll eventually either annihilate to heat the Earth or form a small black hole inside the Earth. We'll talk about the second option in a little bit. But first, I should note that all of these processes occur for just a model where there's a low velocity dark matter standard model cross section. The same thing, of course, would apply for the sun. The dynamics are all the same. And the same thing would apply for white dwarfs and neutron stars, which is actually how I started looking into these sorts of dynamics. As I mentioned before, for high mass dark matter and its capture on Earth, it's actually especially important to get the low velocity portion of the dark matter distribution correct. And to do that, you're going to have to put in another theta function if you're used to dealing with these sorts of Maxwell-Boltzmann distributions, because you need to take into account the fact that the dark matter has a certain minimum velocity, which is quite important if it needs to scatter a lot of times in order to be captured. So if you have dark matter and it forms a sphere of particles at slowly coalesce inside the Earth, eventually these dark matter particles will start to annihilate, if they can annihilate, and you'll reach this sort of annihilation capture equilibrium, and you'll heat the Earth. And so this was a concept that was actually introduced in 2007 by Mack, Beacom, and Bertone, and that is that you can set bounds on dark matter parameter space by considering annihilation and heating of the Earth. I did a sort of redo of this analysis with some grad students where we did a more detailed model of the Earth, and we looked at a wider range of dark matter models and dark matter annihilation cross sections. But let's say that the dark matter doesn't annihilate and it just sort of keeps on collecting inside the Earth. Well, if that occurs, then eventually they'll collapse. And there are some conditions you have to satisfy in order to have the dark matter collapsing inside the Earth. You have to form enough dark matter in there that it becomes self-gravitating. The dark matter fundamental mass has to be large enough that it would collapse even under its own Fermi degeneracy pressure in the case that it's a fermion. But you can form a black hole. The black hole formation time depends on the dark matter nucleon scattering cross section and the dark matter mass, and whether you're sitting, for instance, inside the Earth or the sun. The black hole evaporation time can also be parameterized in terms of the mass of the dark matter and the cross section of the dark matter, because that will determine what size black hole you make. The upshot really is just that higher mass dark matter implies smaller black holes because you have less Fermi degeneracy pressure and you thermalize into a smaller region inside your planet or your star. And the other thing you need to know is that if you have a smaller black hole, it's going to evaporate. So with just that information in hand, we can move on to bounds you can set using black holes formed inside the sun and the Earth. In the yellow region here, you would be forming black holes that would destroy the sun, and that didn't occur because we're all sitting here. For the blue region, you would also be forming black holes that would destroy the Earth. So that's very dramatic. And in this red region, you'd be forming black holes that would be small enough that they would evaporate and they would heat the Earth more than you see the Earth currently heated. And so this sets some nice exclusions. I would note that there's a really tiny sliver of parameter space here where you can consider a black hole that has appeared but hasn't grown enough yet to destroy the Earth. But we can thank all these direct detection experiments and the sun, because that region of parameter space is already excluded by a number of direct detection experiments. So thank you, we're safe from the black holes formed from heavy dark matter in the Earth. Last thing that might have occurred to you is if you have small black holes forming in the sun, they could evaporate and give you neutrinos. And so that's something we also considered. You get a flavor universal neutrino spectrum. They'd be directional, just like from dark matter annihilating in the sun. And so you can use ice cube data that was used to set dark matter, bounds on dark matter annihilating in the sun, also to bound the scenario that dark matter forms small black holes that evaporate in the sun and give you a neutrino signature. This was work I did with some grad students that I've already mentioned, and also Joachim Kopp and Toby Overkuch. Okay, great. The last thing I'm going to tell you about today, in the same vein of dark matter in stars, is dark matter in neutron stars. And what I'd like to talk to you about is neutron stars as dark matter's nature's, dark matter accelerators. So neutron stars accelerate dark matter to even up to beyond what you would think of as a freeze out speed, which is maybe more around like 0.1 or 0.3 times c, depending on your model. They're dense and they accept a large dark matter flux. Of course, they have normal stellar parameters, besides the fact that they're very dense. So they have a very large fiducial mass to interact with. I'm just going to mention that there have been a ton of studies over the last few decades looking at how you can use neutron stars to look for dark matter. I've listed an incomplete list here. You can search for all sorts of different kinds of dark matter. I'll try to give you a sense of why that's the case when it comes to neutron stars now by focusing in on Higgsinos. But for the moment, let me tell you about our twist on this, which was dark matter kinetic and annihilation heating of neutron stars. So if you just think about the energy dark matter has as it falls into the neutron star, it turns out that's enough to make some money with. Because if you just converted that energy into neutron star heating, you would heat up neutron stars to 1750 Kelvin. Yeah, we have the bells as well. So thanks, Keith, 5 minutes. And if all the dark matter is captured and annihilates, you'd actually heat the neutron star to 2500 Kelvin. You can compare this to what you expect for typical neutron stars around us to have after a billion years, which is around 100 Kelvin temperature. So this plot is showing you what sensitivity you would get if dark matter heated neutron stars. Well, if you were able to set a bound on dark matter, set a bound using neutron stars by seeing a neutron star that had a temperature less than 1750 Kelvin, then that would tell you that essentially any dark matter in this parameter space and above would have heated neutron stars to above that temperature. So this clocks in at around 10 to the minus 45 centimeters squared over a wide range of masses. And then as you go to higher masses, you have to think about multiscattering in order to capture the dark matter and harness all of its kinetic energy. But then we can talk about the Higgsinos and use them as a case study to see sort of the power that neutron stars have for searching for dark matter. So while Higgsino dark matter at very low velocities would have a cross-section that's extremely tiny, if you speed it up to 0.7 times the speed of light, it can overcome that kinematic threshold we were talking about, and you can turn x1 into x2 particles. And so its effective cross-section is like 10 to the minus 39 centimeters squared, which is well more than enough for it to be captured inside of a neutron star. And we can get into more of the details if you want during the question period about how that would happen through a Z or a W boson and whether that would occur through the x1 to x2 or the x1 to x plus splitting of the Higgsino. But that's a bit of a technical detail. The point is you can capture the Higgsino dark matter quite neatly inside of a neutron star. But then there's an additional question, which is it just going to kinetically heat the neutron star by hitting neutrons in the neutron star and heating them up? Or is it going to annihilate and heat the neutron star even more? And that's actually a bit of a hard question to answer, because when you typically do these sorts of analyses, you think about what the low velocity cross-section is for your dark matter when it's settling at the core of whatever star you're thinking about, in this case, the neutron star. And again, that's actually a cross-section that's not well known and really only has an upper bound to its cross-section because of accidental cancellations between PDF nucleon form factors. And so a solution that I explored a few years ago is to think about capture and annihilation in the neutron star pasta region. So I'm going to have to tell you a little bit about what the neutron star pasta region is. So inside a neutron star at the very core, it's what you expect, or actually it could be a lot of things, but if you want a standard neutron star model, it's what you expect. It's basically a sea of neutrons. But as you get to the outer layers, you have these globules that look at the very outer surfaces like nuclei. But as you get farther and further in, they become like deformed, elongated nuclei. And then as you get even farther in, they become very, very stretched out nuclear material that forms strings, which are called spaghetti, and then sheets, which are called lasagna, and so forth. And so a really fun thing we did was we said, OK, so we're not sure about what's going to happen with the Higgsinos at low velocity inside the neutron star. But what we can think about is dark matter and WIMPs in general interacting still at very high speeds, which has a really interesting relationship to their speed in the early universe, because you also expect that speed during freeze out to be like 0.1 times the speed of light. And so whatever dynamics you had that set your freeze out abundance should also be occurring for the WIMPs when they're in this phase where they're orbiting around in the sort of central 10-kilometer shell of the neutron star. So in that region, you should expect that dark matter annihilates much as it does in the early universe. And what we showed was that you'll get annihilation that actually increases as this thing shrinks down further. And so you can use annihilation in the pasta region as a limiting case. And when you put that all together, what you find is that you get an equilibration time for your dark matter, and for your Higgsino dark matter even, that's less than 10,000 years, which is well short enough to basically guarantee that the Higgsinos annihilate inside the neutron star, and they heat it up to a temperature of 2,500 Kelvin. Why is it important to think about, what's the maximum temperature that these Higgsinos would heat the neutron stars to? Well, when you want to go and look for a very cold neutron star, and this is something we're still doing research on actively right now, there are a number of methods you would, bring to bear on that. One is you would try to find a neutron star as close to Earth as you possibly could. There are actually some very exciting pulsar candidates within about 100 parsecs. Then you would want to do follow-on astronomy with that with an infrared telescope. It can be a sort of near IR telescope even for the case of annihilation heating. And it can take a very long time to actually look at the neutron star and determine a good lower bound on its temperature. And so if you know that it's heated to 2500 Kelvin, that actually makes a huge difference to how long you would have to stare at that sort of neutron star. And so these are just some rough estimates for us looking into looking for dark matter with neutron stars. So that brings me to my summary slide. Some things I've talked about today are Higgsino dark matter at high recoil and neutron stars, heavy composite formation and multiscatter detection, dark matter forming black holes in the sun and earth, and thermal neutron star searches for dark matter. Happy to take questions now, so thanks very much.
Okay, well, thanks a lot, Joe, and we should all thank Joe for a great talk. So at this moment, we have one question from Jim Klein. He says, sorry if you said this and he missed it, but for accumulation of dark matter in the Earth or the sun, what about absorption of larger clumps? He says, I think you considered absorption of elementary dark matter particles, but he's wondering about the clumps.
That's right. Yeah, so I have a backup slide about that I'll switch to. So if I think about composite dark matter, so if I think about larger clumps, this is what it looks like, which is actually quite nice. You'll see that because the sun and the Earth are large bodies that have a large flux acceptance of dark matter, you can think about going to very large composite dark matter masses. So here we've shown what's going on if you consider composites made of fundamental fermions that have masses 10 to the 9 GeV, 2 times 10 to the 11 GeV, and 10 to the 12 GeV. And different things happen depending on what the fundamental state inside the composite or the clump that you've captured is. Because if, for instance, you have a lower mass fundamental state making up your composites, you'll have to accumulate a lot of it before you overcome Fermi degeneracy pressure and form a black hole inside the Earth or the sun. This means that you'll be looking at bounds where you're mostly destroying either the Earth or the sun, which we can rule out because they're still around. If you think about slightly heavier dark matter, then you open up the possibility that it will create a smaller black hole that evaporates. And over most of the parameter space, indeed, that's what happens, although there's still some parameter space here where you're forming destructive black holes inside the sun. So there you're going to look for Earth heating and neutrino type signatures. But yeah, it's quite nice that you can get up to very large composite masses, all the way up to like 10 to the 38 GeV in that case. Yeah.
Okay. We also have a question from Iris Freitas, and he will just ask it directly himself.
Yeah, sorry, as an organizer, I can't write in the Q&A, but I'll just talk. I had a question about these black hole limits. It seems to be in a parameter space that the lower boundary, both for the case where Earth is destroyed and where Earth is heated too much, like they connect like almost on a straight line. So how can one understand that in both cases it's pretty much at the same place? Is it just that this is the threshold where black holes form?
So I would be remiss if I didn't channel my colleagues on this and point out that, in fact, they're not quite straight lines. There is a tiny little inflection point here.
Sure.
And there's an inflection point there, which is actually very important because that's a crossing point at which you're limited by Fermi degeneracy pressure or self-gravitation of the clump of dark matter you're forming in the center. But that's the central sort of piece that tells you why these have roughly the same slope. The question is, are you forming a black hole inside of the Earth or the sun? And then something I didn't go into detail with is, in this region, the black hole is large enough that its growth rate from Bondi accretion, because its area is larger, exceeds its Hawking evaporation rate. And so it just grows and destroys the star. Here, you've also just formed a black hole, but it's small enough that it can't accrete enough baryons. Given how fast it's evaporating. So it just sort of evaporates away. So that's why these slopes are similar, although not equal. The structure you're noticing here in the Earth that you don't see for the sun is because the Earth actually has an iron core. And so you're actually seeing capture on that iron core there. Yeah. Did that answer your question? Yeah, okay.
Okay, so far, now we have connections to geology. In any case, I don't think we have any further questions. We're doing very well on time, so let's just proceed. Oh, we do have one question. Is there any bound on mass of dark matter which will capture by in neutron stars, NS?
That's a great question. I would have to think about that a little bit carefully. I'd expect that if I'm thinking about a billion-year time scale, the effective area for the neutron star, when you take into account sort of its gravitational capture radius, is going to be similar to, it's actually going to be a little bit less than a main sequence star. So I'd expect that to be up here in the 10 to the 36 to 10 to the 40 GeV range, but I'd have to sit down and do that carefully, and you'd have to think about how long this neutron star has existed exactly in order to figure out what the upper mass reaches of a neutron star, but it should be roughly in that range.
Okay, so let's move on to the next speaker. Thanks again